Hello and welcome. This is going to be a short presentation to help you understand 3 different ways to understand bearing tones. Here we have a rolling element bearing with a defect on the outer race at the bottom. And as you can see, as this rotates around and the balls hit that defect, they make a little pinging sound. Ping, 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 ping. And this is called a bearing tone. This is the source of vibration in the ball bearing for this type of defect. And we're going to discuss 3 different ways we can look at this defect. Now, the first way is called the time waveform. And as we see this graph being plotted, we have a big sine wave, which is the shaft turning around. That's this wave. And then we also can see each ball hitting the fault at the bottom makes a little click. 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 And as we said, we can see these events, or these impacts, directly in the time waveform. Now, if we know the amount of time between clicks, or between impacts, we can calculate the frequency, or the frequency of impacting. And this brings us to the second way that we can talk about this information. We can present the same information in something called a spectrum. A spectrum is a plot of frequency versus amplitude. And down here what we see is the spectrum of the waveform above. This green peak over here coincides with the shaft rate, or this slower vibration here. The yellow peaks coincide with the rate of the balls hitting the fault on the outer race. These other yellow peaks are called harmonics. They are multiples of this first one, and they come out of this process of converting from a time waveform to a spectrum. But all of these yellow peaks are related to the rate at which that outer rate defect is getting struck by the balls. Here is a real example of actual data from a machine that describes the same thing. Here is the time waveform, and we can see there's a low frequency here, which is the shaft rate, and then we can see an impact, 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 etc. These are repetitive hitting. Down in the spectrum, this peak coincides with the shaft rate, and this one marked in red coincides with this rate, or the frequency at which this is getting hit. And again, that is our outer race defect frequency in this case. These peaks over here are harmonics, or multiples of this one. They're also related to that rate at which that fault is getting hit by the balls. So that describes 2 ways to view that information. The first, again, is in the time waveform, where we see the impacts directly, as we can see here. The second way was looking at it in the spectrum. And the spectrum is basically asking, what is the rate at which these balls are hitting this fault? Now, the third way is to look at or listen to the sound that is made when a ball hits the defect. We can think of the ball bearing like a bell, and when the ball hits that fault, the bell rings. And when it rings, it makes a sound, and that sound is a high frequency, and that's what we are seeing here circled. So let's look at this high frequency a little closer. Again, This is the sound the bearing makes when it gets hit. Ping! And this is a high frequency. Now, what we can do is we can use filters to filter out all of the low frequency information from this machine, where basically all of the vibration and noise the machine is creating, but not that high frequency sound that the bearing makes when it gets hit. And then we can ask, using filters, what is the rate of repetition or the frequency of the sound of the bearing ringing? So again, when I hit it once, it makes a sound. And with filters I can ask, how frequently is that high frequency sound occurring? Bing, 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 bing. And this technique is called demodulation. Again, the result of this is to find out what is the rate at which that dinging is happening, and that is our bearing tone frequency. It is a different way to get to the same information. Okay, this information can be presented in what's called a demodulated spectrum, or an enveloped spectrum, and this is in frequency versus amplitude. And what we can see here is the frequency, or the rate at which that defect is getting struck. That's the rate at which we hear the sound of the bearing happening, or getting hit. And because we've filtered out all the other vibration from the machine, this technique is very, very sensitive. We filter out all the other vibration, and then we can zoom in on the sound of that bearing ringing, and then ask again using filters, what's the rate at which it's getting rung? Now, because we're filtering out all that other noise, we can detect problems very early with this technique, up to even a year or more before the problem is really a problem that needs to be attended to. On the other hand, as the problem gets worse, and that's what we're seeing down here, these peaks will get higher and higher, but as it gets really bad, the noise down here will begin to raise until we're left with only noise, which is to say the demodulation goes away. So as the problem gets worse, we will not see usable information in the demodulated spectrum. So now let's do a quick review of what we've discussed. We've basically shown three different ways to look at a bearing tone. The first way was in the waveform, where we are viewing the impacts, and that's the balls hitting the fault, directly. Every time there's an impact, we see it very clearly in the time waveform. In the second method, we looked at a spectrum, and this is asking what is the rate at which the balls are hitting that defect. And that is a graph of frequency versus amplitude. The third way to look at these bearing tones is with demodulation. And this is a way of asking, using filters, what is the sound the bearing makes when it gets hit, and how frequently is that sound occurring? Which is the same as asking, what is the rate at which the defect is getting struck? But again, it's a different way to come to that information, and it's a more sensitive way. Well, I thank you very much for attending this presentation. A little bit about the Mobius Institute. The Mobius Institute provides vibration and shaft alignment courses, among other things. These courses are given in public venues around the world. We offer private on-site courses. We also offer our courses via the internet or on CD. We provide certifications in accordance with ISO and ASNT, and our website is mobiusinstitute.com. A little bit about me. My name is Alan Friedman. I worked for DLI Engineering for 15 years, and in that job I traveled around the world and helped install vibration monitoring programs in hundreds of facilities. I also taught vibration analysis courses to thousands of students worldwide. I've been working with the Mobius Institute for 2 years, but we've been friends for many more years than that. My email address can be found at the bottom if you have any questions. Thank you again for your time.